Good day everyone, I am Michelle Gado Taiko and today I will be discussing about fluid mechanics. So let us first define what is a fluid. You will recall from physics that a substance exists in three primary phases: the solid, liquid, and gas. We already have a common sense idea of when we are working with a fluid as opposed to a solid. Fluids tend to flow when we interact with them, while solids tend to deform or bend. Fluid is a substance which has no definite shape and will continuously deform or flow whenever an external force is applied to it. It cannot preserve its shape unless it is restricted into a particular form depending upon the shape of its surroundings. Fluids comprise the liquid and gas phases of physical forms in which matter exists. So, in a liquid, groups of molecules can move relative to each other, but the volume remains relatively constant because of the strong cohesive forces between the molecules. As a result, a liquid takes the shape of the container it is in, and it forms a free surface in a larger container in a gravitational field. On the other hand, a gas expands until it encounters the walls of the container and fills the entire available space. This is because the gas molecules are widely spaced and cohesive forces between them are very small. Unlike liquids, a gas in an open container cannot form a free surface. So what about the mechanics? So mechanics is the oldest physical science that deals with both stationary and moving bodies under the influence of forces. The branch of mechanics that deals with the bodies at rest is called statics, while the branch that deals with bodies in motion is called dynamics. So now let us define fluid mechanics. So fluid mechanics is the science that deals with the behavior of fluids at rest or in motion, and the interaction of fluids with solids or other fluids at the boundaries. Fluid mechanics is also referred to as fluid dynamics by considering fluids at rest as a special case of motion with zero velocity. There are two branches of fluid mechanics. First is the fluid statics, and the second one is the fluid dynamics. The fluid statics or the hydrostatics is the branch of fluid mechanics that studies fluids at rest. It embraces the study of the conditions under which fluids are at rest in stable equilibrium, and is contrasted with fluid dynamics, the study of fluids in motion. Hydrostatics offers physical explanations for many phenomena of everyday life, such as why atmospheric pressure changes with altitude, why wood and oil float on water, and why the surface of water is always level whatever the shape of its container. Hydrostatics is fundamental to hydraulics, the engineering of equipment for storing, transporting, and using fluids. It is also relevant to some aspects of geophysics and astrophysics. For example, in understanding the plate tectonics and anomalies in the Earth's gravitational field, to meteorology, to medicine in the context of blood pressure, and many other fields. So fluid dynamics is a subdiscipline of fluid mechanics that deals with fluid flow, the science of liquids and gases in motion. Fluid dynamics offers a systematic structure which underlies these practical disciplines that embraces empirical and semi-empirical laws derived from flow measurement and used to solve practical problems. The solution to a fluid dynamics problem typically involves calculating various properties of fluids such as velocity, pressure, density, and temperature as functions of space and time. The fluid dynamics itself is also divided into several categories. The study of motion of fluids that are practically incompressible, such as liquids, especially water and gases at low speeds, is usually referred to as the hydrodynamics. A subcategory of hydrodynamics is hydraulics, which deals with liquid flows in pipes and open channels. Gas dynamics deals with the flow of fluids that undergo significant density changes, such as the flow of gases through nozzles at high speeds. The category aerodynamics deals with the flow of gases, especially air, over bodies such as aircraft, rockets, and automobiles at high or low speeds. Some other specialized categories such as meteorology, oceanography, and hydrology deal with naturally occurring flows. So now, let us know the history of the fluid mechanics. So here are the key theories in the history of fluid mechanics. During the 390 BC, Plato, a Greek philosopher, describes the origins of rivers as water escaping through holes in the ground. In 250 BC, Archimedes publishes Floating Bodies, in which he discusses the principles of buoyancy and hydrostatics. In 200 BC, Chinese scholars discovered that tides are connected to the lunar cycle. In 100 BC, Greek philosopher Posidonius discovers tides are connected to the lunar cycle. During 1643 AD, Evangelista Torricelli develops the relationship between pressure and velocity of fluids for free jets. In 1738 AD, Daniel Bernoulli publishes Hydrodynamica, which discusses the pressure and velocity of fluids and delineates the Bernoulli equation. In 1768, Antoine Chiezi develops relationships for open channel flow, and in 1839, Gottlob Heinrich Ludwig Hagen describes laminar flow properties. During the 1840 AD, Jean-Louis Poiseuille describes laminar flow properties. In 1850 AD, Rodolphe Clausius develops kinetic theory of gases. In 1877 AD, J. Boussinesq describes eddy viscosities and turbulent flows. In 1883, Osborne Reynolds describes the differences between laminar and turbulent pipe flow. In 1889 AD, R. Manning develops a modified equation describing open channel flow. In 1891 AD, Samuel Langley publishes experiments in aerodynamics. In 1895 AD, Osborne Reynolds describes turbulent shear stresses. And in 1904 AD, Ludwig Prandtl develops solutions to Navier-Stokes equations for boundary layer flow. During 1908, Paul Richard Heinrich Blasius developed solution to boundary layer equations for flow past a flat plate. During 1918, Ludwig Prandtl develops theory of flow over airplane wings. In 1919, Robert Goddard publishes a method of reaching extreme altitudes. In 1921, Hermann Oberth publishes the rocket into interplanetary space. In 1933, J. Nikoradze describes the relationships between pipe flow, friction factor, and Reynolds number. And in 1944, L. Moody summarizes relationships between pipe flow, friction factor, and Reynolds number, and develops the Moody chart. Fluid mechanics is widely used both in everyday activities and in the design of modern engineering systems, from vacuum cleaners to supersonic aircraft. Therefore, it is important to develop a good understanding of the basic principles of fluid mechanics. To begin with, fluid mechanics plays a vital role in the human body. The heart is constantly pumping blood to all parts of the human body through the arteries and veins, and the lungs are the sites of airflow in alternating direction. Needless to say, all artificial hearts, breathing machines, and dialysis systems are designed using fluid dynamics. An ordinary house is, in some respects, an exhibition hall filled with applications of fluid mechanics. The piping system for cold water and natural gas, and sewage for an individual house and the entire city are designed primarily on the basis of fluid mechanics. The same is also true for the piping and ducting network of heating and air conditioning systems. A refrigerator involves tubes through which the refrigerant flows, a compressor that pressurizes the refrigerant, and the two heat exchangers where the refrigerant absorbs and rejects heat. Fluid mechanics plays a major role in the design of all these components. Even the operation of ordinary faucet is based on fluid mechanics. We can also see numerous applications of fluid mechanics in an automobile. All components associated with the transportation of the fluid from the fuel tank to the cylinders, the fuel line, the fuel pump, fuel injectors, or the carburetors, as well as the mixing of fuel and the air in the cylinders and the purging of combustion gases in the exhaust pipes are analyzed using fluid mechanics. So fluid mechanics is also used in the design of the heating and air conditioning system, the hydraulic brakes, the power steering, the automatic transmission, and the lubrication system, the cooling system of the engine block, including the radiator and the water pump, and even the tires. On a broader scale, fluid mechanics plays a major part in the design and analysis of aircraft, boats, submarines, rockets, jet engines, wind turbines, and biomedical devices, the cooling of electronic components, and the transportation of water, crude oil, and natural gas. It is also considered in the design of building bridges, buildings, and even billboards to make sure that the structures can withstand wind loading. Numerous natural phenomena such as the rain cycle, the weather patterns, and the rise of groundwater to the top of trees, winds, ocean waves, and the currents in large water bodies are also governed by the principles of the fluid mechanics. Fluid flow is often confined by solid surfaces, and it is important to understand how the presence of solid surfaces affects fluid flow. We know that water in a river cannot flow through large rocks and goes around them. That is, the water velocity normal to the rock surface must be zero, and water approaching the surface normally comes to a complete stop at the surface. What is not so obvious is that water approaching the rock at any angle also comes to a complete stop at the rock surface, and thus the tangential velocity of water at the surface is also zero. Consider the flow of a fluid in a stationary pipe or over a solid surface that is non-porous or impermeable to the fluid. All experimental observations indicate that a fluid in motion comes to a complete stop at the surface and assumes a zero velocity relative to the surface. That is, a fluid in direct contact with a solid sticks to the surface due to viscous effects, and there is no slip, and this is known as the no-slip condition. So, in this photo, this is obtained from a video clip that clearly shows the evolution of a velocity gradient as a result of the fluid sticking to the surface of a blunt nose. The layer that sticks to the surface slows the adjacent fluid layer because of viscous forces between the fluid layers, which shows the next layer and so on. Therefore, the no-slip condition is responsible for the development of the velocity profile, and the flow region adjacent to the wall in which the viscous effects are significant is called the boundary layer. The fluid property responsible for the no-slip condition and the development of the boundary layer is the viscosity. A fluid layer adjacent to a moving surface has the same velocity as the surface. A consequence of a no-slip condition is that all velocity profiles must be zero values with respect to the surface of the points of contact between the fluid and a solid surface. So another consequence of the no-slip condition is the surface drag, which is the force a fluid exerts on a surface in a flow direction. So when a fluid is forced to flow over a curved surface, such as the backside of a cylinder at sufficiently high velocity, the boundary layer can no longer remain attached to the surface, and at the same point, it separates from the surface, a process called flow separation. So we emphasize that no-slip condition applies everywhere along the surface, even downstream of the separation point. So earlier, we defined fluid mechanics as the science that deals with the behavior of fluids at rest or in motion, and the interaction of fluids with solids and other fluids at the boundaries. There is a wide variety of fluid flow problems encountered in practice, and it is usually convenient to classify them on the basis of some common characteristics to make it feasible to study them in groups. There are many ways to classify fluid flow problems, and here are some general categories. First is the viscous and the inviscid regions of flow. When two fluid layers move relative to each other, a friction force develops between them, and the slower layer tries to slow down the faster layer. This internal resistance to flow is quantified by the fluid property called viscosity, which is the measure of internal stickiness of the fluid. Viscosity is caused by cohesive forces between the molecules in liquids and by molecular collisions in gases. There is no fluid with zero viscosity, and thus all fluid flows involve viscous effects to some degree. Flows in which the frictional effects are significant are called viscous flows. However, in many flows of practical interest, there are regions where viscous forces are negligibly small compared to the inertial of pressure forces. Neglecting the viscous terms in such inviscid flow regions greatly simplifies the analysis without much loss in accuracy. The development of viscous and inviscid regions of flow as a result of inserting a flat plate parallel into a fluid stream of uniform velocity, as shown on the picture below. The fluid sticks to the plate on both sides because of the no-slip condition, and the thin boundary layer in which the viscous effects are significant near the plate surface is the viscous flow region. The region of flow on both sides away from the plate and unaffected by the presence of the plate is the inviscid flow region. A fluid flow is classified as being internal or external, depending on whether the fluid is forced to flow in a confined channel or over a surface. The flow on an unbounded fluid over a surface such as a plate, a wire, or a pipe is external flow. The flow in a pipe or duct is internal flow if the fluid is completely bounded by solid surfaces. Water flow in a pipe, for example, is internal flow, and airflow over a ball or over an exposed pipe during a windy day is external flow. So as you can see on the figure or the picture below, the flow of liquids in a duct is called open channel flow if the duct is only partially filled with the liquid and there is a free space. The flows of water in rivers and irrigation ditches are examples of such flows. Internal flows are dominated by the influence of viscosity throughout the flow field. In external flows, the viscous effects are limited to boundary layers near solid surfaces and to wake regions downstream of bodies. The flow is classified as being compressible or incompressible depending on the level of variation of density during flow. Incompressibility is an approximation, and a flow is said to be incompressible if the density remains nearly constant throughout. Therefore, the volume of every portion of fluid remains unchanged over the course of its motion when the flow is incompressible. The densities of liquids are essentially constant, and thus the flow of liquid is typically incompressible. Therefore, liquids are usually referred to as incompressible substances. When analyzing rockets and spacecraft and other systems that involve high-speed gas flows, the flow speed is often expressed in terms of the dimensionless Mach number, defined as speed of flow divided by speed of sound. The speed of sound, whose value is 346 meters per second in air at room temperature at sea level. So the flow is called sonic when the Mach number is equal to 1, and the flow is called subsonic if the Mach number is less than 1. The flow is called supersonic if the Mach number is greater than 1, and the flow is called hypersonic flow if the Mach number is much greater than 1. Some flows are smooth and orderly, while others are rather chaotic. The highly ordered fluid motion characterized by a smooth layer of fluid is called laminar. The word laminar comes from the movement of adjacent fluid particles together in laminates. The flow of high viscosity fluids such as oils at low velocities is typically laminar. The highly disordered fluid motion that typically occurs at high velocities and is characterized by velocity fluctuations is called turbulent. The flow of low viscosity fluids such as air at high velocities is typically turbulent. The flow regime greatly influences the required power for pumping. A flow that alternates between being laminar and turbulent is called transitional. A fluid flow is said to be natural or forced depending on how the fluid motion is initiated. In forced flow, a fluid is forced to flow over a surface or in a pipe by external means, such as a pump or a fan. In natural flows, any fluid motion is due to natural means such as the buoyancy effect, which manifests itself as the rise of warmer fluid and the fall of the cooler fluid. Next is the steady versus unsteady flow. The term steady implies no change at a point with time. The opposite of steady is unsteady. The term uniform implies no change with location over a specified region. These meanings are consistent with their everyday use. The terms unsteady and transient are often used interchangeably, but these terms are not synonyms. In fluid mechanics, unsteady is most general term that applies to any flow that is not steady, but transient is typically used for developing flows. When a rocket engine is fired up, for example, there are transient effects. The pressure builds up inside the rocket engine and the flow accelerates until the engine settles down and operates steadily. The term periodic refers to the kind of unsteady flow in which the flow oscillates about a steady mean. Many devices such as turbines, compressors, boilers, condensers, and heat exchangers operate for a long period of time under the same conditions, and they are classified as steady flow devices. Note that the flow field near the rotating blades of a turbo machine is of course unsteady, but we consider the overall flow field rather than the details at some localities when we classify devices. During steady flow, the fluid properties can change from point to point within a device, but at any fixed point they remain constant. Therefore, the volume, the mass, and the total energy content of a steady flow device or flow section remain constant in steady operation. A flow field is best characterized by the velocity distribution, and thus a flow is said to be 1, 2, or 3-dimensional if the flow velocity varies in 1, 2, or 3 primary dimensions respectively. Consider a steady flow of a fluid through a circular pipe attached to a large tank. The fluid velocity everywhere on the pipe surface is 0 because of the no-slip condition, and the flow is 2-dimensional in the entrance region of the pipe. Since the velocity changes in both the R and Z directions, the velocity profile develops fully remains unchanged after some distance from the inlet. And the flow in this region is said to be fully developed. A flow may be approximated as 2-dimensional when the aspect ratio is large and the flow does not change appreciably along the longer dimension. For example, the flow of air over a car antenna can be considered 2-dimensional except near its end, since the antenna's length is much greater than its diameter and the airflow hitting the antenna is fairly uniform. So that ends my discussion about the fluid mechanics. Thank you for watching.